All right. And if you're not done copying, just I'm still staying on this page, so you'll have more time. All right, so we're going to use our rate of change formula. And I'm keeping it here for now, but eventually you guys will have to memorize this. Rate of change formula. And I'm going to find the rate of change between week 1, or x1, and x equals 2. I'm going to start with those two values. So here I have x1, x2, y1, y2, and I'm going to just plug all of that into my rate of change formula. So I have y2 minus y1, so that's 4 minus 1 over 2 minus 1. 4 minus 1 gives me 3. 2 minus 1 gives me 1. So my rate of change between the first 2 points is 3. Okay, so that's the first thing. And now I'm going to do it the same exact thing, but instead of using the first 2 points, I'm going to use the second point and the third point. So now I'm looking at the 2 and the 3. And I do the same thing. y2 minus y1 would be 9 minus 4. x2 minus x1 would be 3 minus 2. 9 minus 4 gives me 5, and 3 minus 2 gives me 1. So the rate of change between those 2 points is 5. Okay, so that's what I want you guys to do that now with table B and table C. So you're going to find the rate of change between the first set of points, the first 2, and then do the rate of change between the second 2 points. And then once we find that for all 3 tables, we're going to talk about any patterns we notice. So I want you guys to go ahead and take 4 minutes. 4 minutes to find those rates of change for table B and for table C. And see what we got. So in table B, I'm starting with the first 2 points, which is 1 comma 3 and 2 comma 6. So I plug that straight into my formula. I have 6 minus 3 over 2 minus 1. 6 minus 3 is 3. 2 minus 1 is 1. So I get m equals 3. Then I do my second 2 points. So I have 2 and 6, and 3 and 9. And again, I just plug it right into the formula. y2 minus y1, that's going to be 9 minus 6 over 3 minus 2. 9 minus 6 is 3. 3 minus 2 is 1. So again, I get m equals 3. Okay, so that was for B. And then for C, I'm doing the same thing. I just have different numbers. So my first 2 points, and I'm kind of running out of room. I hope I can fit everything, but I get 8 minus 1 over 2 minus 1. 8 minus 1 is 7. 2 minus 1 is 1. So I get m equals 7. And for the second set of points, I get 27 minus 8 over 3 minus 2. What's 27 minus 8?
19.
Good, 19. And then 3 minus 2 is 1. So I get m equals 19. All right. So here I have all of those values for all 3 tables. Do you guys notice something interesting that might have happened?
Yeah.
What happened?
In table B, they had the same rate of change.
Perfect. In table B, we had the same rate of change between the first set of points and the second set of points. All right, so that is going to tell us something very, very important. And what that means is that this relationship, this function, is a linear function. So I'm going to label this one as linear. And I'll talk a little bit more about what that means. But for now, just know that that means that this one is linear, and the other 2, since they did not have the same rate of change, these are nonlinear. Okay, so we got nonlinear and linear. And in 1 second, I'm just gonna, in the next slide, I'll explain what it means to be linear functions. But do I have any questions on how I got those answers for rate of change? Or anything else? Awesome. All right, so what is a linear function? Let's find out. Can I have a volunteer just read this scenario? I have a graph here and there's a scenario. So who would like to read?
A race car can travel up to 210 miles per hour. If the car could travel continuously at this speed, y equals 210x gives the number of miles y that the car would travel in x hours. Solutions are shown in the graph below.
Awesome. So this graph is showing us basically how fast that car, or like the distance that the car is traveling in a certain amount of time. And before I go on, what do you guys notice about this graph or this set of points? What kind of path does it make?
They make like a line.
Yeah, they make a line, a straight line. So if I connected all of them, I would get a nice straight line. Let me do that a little bit better. Okay. And that is where we get the idea of linear functions. So the word linear comes from the word line. And yes, okay, so I'm seeing in the chat, Alyssa is saying that this has a constant. This is constant. Let me write this down. And that's a really good key word that maybe you remember from the last chapter. Anytime you have a straight line on a graph, that's called a constant rate, or it has a constant pattern. So this is a constant rate. All right, so I'm going to quickly read the bottom here. The graph of the car's speed is a function because every x value is paired with exactly one y value, which we already know that a function has to pass what's that test that it has to pass?
Vertical line test.
Yeah, the vertical line test. And this passes the vertical line test, so I know it's a function. And then since it's a non-vertical straight line, that's why we're able to call it a linear function. All right, so again, linear function is going to be a straight line that has a constant rate. So now let's talk about what that looks like in a table. So here I have the same exact graph. I copied the same graph, and I'm just going to put the points down on a table. And I want you guys to copy down just this table right here that I'm about to fill out. And I'm going to fill it out using the points from my graph. So I have 1, 210, 2, 420, 3, 630, 4, 840, and 5, 1050. Okay, so I'm just copying it down. And notice that it's asking me to use the table to check that there's a constant change. So what I need to do, basically, this is asking me like to check that it's linear using math rather than looking at the graph, because on a graph you can basically tell without a problem because you can tell that it's a straight line. But we're going to double check using math. So what we're going to do is we're going to find the constant rate of, or find the rate of change, just like we did in the previous slide. We're going to find it between the first 2 points and then the second 2 points. And then we're going to do it one more time between the third 2 points, because if we notice that it has the same value every time, that's how you can guarantee that it is a linear function. And the reason I want you guys to do it between the first 2 points, second 2 points, and third 2 points is because it's like 3 strikes, you're out kind of thing. Like you want to check 3 times just to make sure that it's perfectly linear. Because sometimes you'll check the first 2 and it's fine. And then the third 2 is the one where it throws you off. So we always want to be perfectly sure. All right, so who can remind me of my formula for rate of change, just so I can write it down?
M equals y2 take away y1.
Good.
Divided by x2 minus x1.
Perfect. So again, that's something that you guys need to make sure we memorize. So from here on out, I'm not going to write it down anymore. You just have to remember it. And I'm going to go ahead and label these so that I can fill it in. All right, so y2 minus y1, that's 420 minus 210 over 2 minus 1. What's 420 minus 210?
210.
210. And 210 divided by 1 is still 210. So my rate is 210. Now, can somebody tell me what the units are?
Miles.
Miles, and remember, we always have
Miles
two.
per hour.
Good, miles per hour. So I'm just going to write MPH, miles per hour. Okay, so I'm all good with the first point, the first 2 points. Now I want you guys to take the next couple minutes to just check if the rate of change is the same between the second 2 points, and then do it one more time between the third 2 points. You should, what you want to get is 210 each time. So I'm just putting 2 minutes on the clock. I should see everybody writing. I can see y'all in the classroom. If I don't see you writing, that's a problem. Good, I'm seeing in the chat lots of correct answers. So I'm just going to start with the next 2 points while everybody finishes. 630 minus 420 over 3 minus 2. What's 630 minus 420?
210.
210. So I get 210 over 1 again. So again, I get 210 miles per hour. And like I said, we always want to do at least 3 checks because you never know when the third one might be the one that's wrong. So we always want to do this 3 times to be absolutely sure. So here we go. Now I have 840 minus 630, and then 4 minus 3. 840 minus 630 gives me
210.
210 again. So you might be like, Miss, this is so easy. This is so obvious. Why did we have to do this so many times? And the reason is because, yeah, of course, this one's kind of easy because you guys already know it's linear because we saw the graph. But we're not always going to get a graph, okay? So sometimes you're going to just have a table and nothing else. And sometimes it might not be such nice, even, pretty numbers. In a couple of examples, you're going to see that sometimes they like to switch it up and make the numbers a little more challenging. So I wanted to give you guys a nice and easy example just so that you can see the pattern. And then we're going to move on to some slightly more difficult ones. But do I have any questions? Okay, so this one's definitely linear.
Wait, Miss.
Mm-hmm.
At first I thought linear meant like the previous number before
Mm-hmm.
minus no wait. The number minus the previous number
Mm-hmm.
would equal the same if you kept going.
Okay,
That's what I thought it
so
was.
yeah, so
Which it is.
another way, which it is, yeah, another way you can think about this, let me just erase all of these. Oh, oops, wait, I didn't want to erase all the numbers. That was dumb. Let me just erase this stuff. Okay. So another way, and I saw a couple people in the chat actually told me this. Let me just move this over. Okay. Oh, whatever, it doesn't want to move. But if you, all you look at is the pattern between one number to the next number, like I said, these are kind of easy numbers. So you can a little bit more easily check and see what happens between one number to the next number. So from 210 to 420, what am I doing?
Adding 210.
Adding 210, exactly. So you can kind of see the pattern this way. plus 210, plus 210, plus 210. And that shows you that it's always going to add 210. And that's great if you have a nice, easy graph, easy table like this one. But like I said, sometimes it's not so obvious. That's why it's always important to check using the formula, because the formula does not lie. The formula will always tell you the right answer. So let's go ahead and look at another example. So now I only have a table. And what I'm going to do is I'm going to use the table first to see if it's linear. And then I'm going to graph it just to double check. Because like I said, a graph can be great because a graph can show you visually, but we want to know mathematically and visually if it's going to be linear. So what I want you guys to do is take 3 minutes to tell me, is this a linear function? So do exactly what we were doing before. Check 3 times, find the rate of change between the first 2 set of points, then the second 2, and then the third 2. And go ahead and tell me if this is a linear function. So 3 minutes. Let me see you guys writing. I see a lot of heads down in the classroom. What's going on inside of there? Come on. Oh, hold up. Sorry. It's loading. Hold on a second. Okay. Okay, about a minute left. Okay. So let's go ahead and check. Time's up. So I put this table here because sometimes you'll get a table that is vertical like this one, and sometimes you'll get a table that's horizontal like this one, but it's important to make sure we know how to work with both. So in this case, what's my x1 and my x2?
-2 and -4.
Good. So those my x1, that's my x2, and then y1 and y2?
3 and -5.
3 and
Negative 5.
Perfect. So 3 and -5. There we go. All right, so between the first 2 points, I'll do this real quick because I know most of you guys already got the answer. But I have 3, and check this out. This is a little tricky because I have negative numbers. So I'm going to show you guys to make sure we're doing this right. I have y2 minus y1 is going to be 3 minus negative 5. So notice what I did. I had to put two minus signs because my formula is y2 minus y1 and then x2 minus x1. But since I have a negative number, I have a double negative because I'm subtracting a negative. So just take that for a second. I'll explain this more in a little second. And then I have negative 2 minus negative 4. Okay, so again, okay, I have a double negative. That's why this is the pattern I get. Now, when I have a double negative, when I'm subtracting a negative number like this, I have two negative symbols in a row. What do they turn into?
A positive.
Mhm. Good. So this is 3 plus 5.
Equals 8.
Right. And then on the bottom, I have negative 2 plus 4.
2.
2. So on the top, I have 8. The denominator, I have 2. And 8 divided by 2 gives me
4.
4.
4. Yeah. So that was my rate of change between the first two numbers. It was a little tricky because of those negative signs. So just make sure that when we're calculating, we have to be very, very careful about that double negative situation. So do I have any questions about just those double negatives? Because I know that can be a little tricky. Awesome. Okay. So we get m equals 4 for the first 2 points. What did you guys get for the second 2 points?
4.
4.
Also
I
4?
got negative 4.
Okay. So was it negative or was it positive?
Positive.
Positive.
It was positive, yeah. So if you got a negative, check your work again, but you should have gotten m equals 4 for the second 2 points. And for the third 2 points, did you also get m equals 4?
Yes.
Yes.
Yes. So we have a constant rate of change, which means that my function is linear. Now I'm going to plot the points down on this graph just to double check. So I have negative 4, negative 5. So if you notice, the x-axis is going by 2s and the y-axis is going by 10s. So I have to be a little bit careful. So I have negative 4 is going to be 1, 2. This is negative 2. Wait, no, this is negative 1, negative 2, negative 3, negative 4. So negative 4 comma negative 5. That's going to be like right here. Then I have negative 2 comma 3, 0 comma 11, 2 comma 19, and 4 comma 27. It's right here. All right. It's not perfect, but it's good enough because this graph was a little bit hard to work with, but this does create, if I had drawn it a little bit better, it would have made a slightly better line, but you can tell that it is going in a linear pattern. It is creating a straight line for the most part. I know I didn't do it perfectly, but that's okay. So do I have any questions so far? How to know if something is linear, how to check if something's linear, how to find constant rate of change. All right. All right, I'm going to do one more, and then from here on out, it's all you guys doing it on your own. So here we go. This is the last one that I'm going to do together. So let's do this one together. Again, here's my formula, y2 minus y1 over x2 minus x1. Starting with, I'm going to check the first 3 points, and then I'm going to graph it to see what it looks like. So starting with the first 2 points, m equals y2 minus y1. So that's 4 minus 1. And then x2 minus x1. So that's 2 minus 1. 4 minus 1 is 3. 2 minus 1 is 1. So I get 3. Just going to quickly move right along because I know you guys probably want to do this on your own. All right, same thing here. Y2 minus Y1, that's 9 minus 4 over 3 minus 2. 9 minus 4 gives me 5. 5 over 1 is 5. So right off the bat, I can tell, is this a linear function?
No.
Right off the bat, I already know this is not a linear function. So I can
Yes,
stop there. Whenever you're checking, if you're checking to see if something is linear and you right away, if you get a wrong, two different numbers, you don't have to keep checking because you already know that it's not going to have a constant rate of change. So this one is nonlinear. And what I want to do is show you guys what a nonlinear function might look like. So I'm going to go ahead and plot these points. So I have 1, 1. And this
Miss,
is
I have a
going,
question.
yes, go ahead, RL.
If it's like if it's linear, then that means that all of the constant
The rate of change.
rate of change
Mhm.
is going to be the same.
The same number, exactly. So notice, I'll quickly go back. In this case, I got 4, I got 4, I got 4. So since I got the same number over and over, that's how I know that this is linear. But here,
Okay.
I got 3, and then I got 5. So right off the bat, I can already tell these are not the same. So that's non-linear.
Thank you.
You're welcome. Alrighty, so let's check and see what's going on here. So I have 1, 1. That's going to be around here. Then I have 2, 4, 3, 9, 4, 16, and 5, 25. All right, so notice this pattern. See what's going on. This is not going to give me a straight line. This is going to give me kind of a curved line. Okay, so there's my graph. All right, so again, graphs are going to be the best way to see visually if you have a linear function or a nonlinear function, but it's important to be able to do it both ways. You have to see it on a graph, but you also have to know how to do it mathematically.
Miss, doesn't matter if it has like negative or if it's a positive.
Nope, that doesn't matter. The only thing that matters is whether you get the same number.
Okay.
Now, I want to show you guys one last thing, and this is something that might confuse you, so I just want to make sure we understand what this means. Is there a pattern here at all?
No, not really.
Not really, right? Because we had +3, then we had +5,
Seven.
+7, plus
I see a pattern.
9. Ooh, okay. What kind of pattern is there?
They're all negative.
Odd
I mean,
They're all odd
Um,
numbers.
Odd
Odd,
numbers. Yeah. So the rate of change kind of has a pattern, but the numbers themselves don't have a pattern. Okay, so that's kind of one thing that might be confusing that I just wanted to clear up. At the end of the day, even though there's a kind of a pattern here, it's not a linear pattern. There's something else going on. And in fact, we'll learn more about these types of functions later, but in case you're wondering, this is called a quadratic function. So it's not linear. This one would be a quadratic function, which for now doesn't really matter. You guys don't have to know what that means, but I know some of you guys like to know the words for different things. All right, so that's all you. So here's what we're gonna do. So first, you're gonna check to see if this is a linear relationship. So do the 3 checks. You should try and see if you get the same rate of change. So I'm gonna give you guys 2 minutes, 3 minutes to go ahead and do that. And you can tell me in the chat, tell me, yes, this is linear, or no, this is not linear. Okay, your 3 minutes begin now. Good. I already have some answers in the chat. Nice. Good job, guys. Good. I already have 4 answers in the chat. Let's see who else can figure this one out. Good. Everybody who has sent me an answer so far has gotten it correct. Good job, guys. Perfect. You didn't even need all that time that I gave you. All right, so I'm going to pause there because I already have so many answers in the chat that I know that you guys are done. All right, so I think everybody agrees. Is this linear?
Yes.
Yes, this is linear. Good. Since it's linear, what is my constant rate?
150.
150.
Good. My constant rate is 150. And can anyone tell me the units?
Profits per week.
Profits per week, and profit is measured using what?
Dollars per week.
Dollars, yeah. So $150 per week. Nice. And you can check that 2 ways. One, you can notice the pattern. So did anyone here notice the pattern first
Yes.
before doing the math? Yeah, what did you guys notice is that this adds by
Add 150.
150.
150.
And it's constant too.
It's constant, exactly. So this is another example where you have kind of easy numbers to work with and you can see the pattern very clearly. And then if it was kind of harder, then I would say, okay, now go check using the formula. But right now we don't need to do that because it's already pretty obvious. But do I have any questions on why this is linear? Cool. All right, so now that I have my constant rate, I know that it's linear. I'm just going to graph it real quick to show visually that it's linear. I should have a straight line. So I have 1, 150, 2, 300, 3, 450, and 4, 600. And the cool thing, once you figure out that something is constant, that something has a constant rate, is that you can use it to see the future. So what this wants us to do is graph the function and then use the graph to predict his business profit 9 weeks after he opens. So I only know up to 4 weeks right now, but when you graph it, what you can do is you can extend the line really far into the future so that you can see what he'll make after 5 weeks, 6 weeks, 8 weeks, and so on. So what do you guys think? What is his profit going to be after 9 weeks based on the graph?
1,350.
1,350. So 9 weeks is right here. And that falls on the 1,350 exactly. And as a reminder, over here, what we just did was we found f of 9. F of 9 equals 1,350. So that's just a quick reminder of function notation, because you can see it both ways. Function notation is just a kind of different way to say if the input is 9, the output is 1,350. So linear functions are great because the pattern that it creates helps us to see the future and predict what's going to happen in the future. Y'all ready for another one? It's too easy, right? All right. Now we got some real numbers. So for this one, I do want you guys to use a calculator. Basically, in this class, anytime that the answer choices have decimals and there's a lot of decimals, you can assume you can use a calculator, but you can always ask me just in case. So now this is for you guys to do. Can I have a volunteer read out the problem for us? Who would like to read?
Mrs. Robinson made the table below showing the yearly balance of her savings account. Interest on the account compounds annually. Thus, Mrs. Robinson's savings account grow at a constant rate? Can it be represented by a linear function?
Good. So we're basically trying to figure out if this is a linear function. All right, so I'm going to trust you guys know what to do. Go ahead and take 3 minutes to figure out and let me know if this is a linear function. If you have questions, you can ask it in the chat. Okay, I'm already getting some answers. I have about a minute left. About 30 seconds. Good. If you have an answer for me, you have 5 seconds to send it in. Awesome. All right. So I had 1, 2, 3. Hold on. All right. I had 1, 2, 3, 4, 5, 6 students answer, and every single person said no, it is not linear. And now let's check and see why it might not be linear. So this is an example where you have kind of harder numbers. You could try to look for a pattern, but at the end of the day, it's going to be easier to just take your calculator out and plug everything into the formula. So I'm going to start with my first 2 sets right here. So I have 463.71 minus 400 over 5 minus 0. 463.71 minus 400 gives me 63.
53.71.
0.71, and then 5 minus 0 is 5. And what do you get here?
12.47.
Say that again, a little louder.
12.742.
Good. 12.714. What are my units here?
No, 42.
Oh, I'm sorry. 12.742. There we go. All right. So what are my units?
Dollars per year.
Very
Dollars
good.
per year.
Dollars per year. All right. So that's my first 2. Let's see what happens when I do my second 2. 573 or 5, sorry, 537.57 minus 463.71 over 10 minus 5. What do I get in the numerator?
73.86.
73. What was it?
0.86.
0.86. Okay. And then 10 minus 5 is 5. And what do I get here?
14.772.
14.772. Okay. So already it's a little bit different, right? One was $12, about $12, and the second was about $14. I want to do one last check just to be sure, because the thing is, I have a real world scenario, right? And in the real world, things are not always going to be perfectly linear. Sometimes if it's close enough, it's good. So I just want to see one last time, see what I get for the third set of points. So 623.19 minus 537.57. Did anyone do this? Did anyone go this far?
No.
Yes.
Some people know because they already checked the first two, right? And they were like, nope, it's not linear. But let's see what happens. So what do I get for the numerator here?
I just didn't go farther from there.
85.62.
85.62 divided by 5 again. What do we get?
17.124.
Good. Okay. So with this, I am definitely sure that this is not linear. The thing is, sometimes, let's say you get like 12 one year, 13 the next year, 12, and then 14. Like if everything was around the same number, sometimes I would say, okay, it's close enough. But here, all three numbers that we get are pretty different. You got 12 the first year, about 12 the first year, about 14 the second year, about 17 the third year. So already I can check. I can be definitely sure that this one's not linear. Alrighty. So the last thing I wanted to say is that, you know how I was saying, okay, what's the pattern? What's the pattern? What's the pattern? And that sometimes you could do it that way. You have to be very careful because here the pattern from the first point to the second point, for example, would be 63.71. But is that the rate of change?
No.
No.
No, because what's also important?
The next one.
Not just the next point, but remember, we got 12.742. How did we get 12.742?
I
Divide that by 5.
We had to divide that by 5, exactly. So the x values also matter because if the x values are changing by something bigger than 1, that's going to be a different number in the end. So even though the pattern is 63.71, the actual rate of change is 12.742 because we had to divide that. So like in the previous problem, this was going by ones. So the pattern was the same as the rate of change. Okay, but since in this table, it's increasing on the x values as well, our pattern is different than the actual rate of change. So that's just one thing to also keep in mind. All right, here's another question. Similar thing, we got big numbers. Here we can use a calculator. The pattern's not going to be as obvious. Who would like to read this one?
For his science. Oh, my bad.
For his science lab assignment, Keone needed to grow cells and recorded his result. At the end of each day, the number of cells at the end of certain days in Keone. I'm having an assignment called Be Back.
Uh-oh. Samantha, you want to pick up where he left off?
Where was he?
Just read A and B.
Can Giovanni's experiment be measured using a linear model? What is the average rate of change in the number of cells from day 2 to day 5?
All right, so this is a two-part problem. First thing is tell me if this is linear. And then the second is we're going to find the average rate of change from day 2 to day 5. So that's kind of going back to what we were doing in the previous class. So just go ahead and start with part 1 or part A. See if this is linear.
Sorry, miss, but something is happening. I'll be back in like 20 minutes.
Okay, I figured something was going on, David. You're good. Come right back when you can. All right. So let's start off with the first question, which is this a linear model? What do you guys think? Linear or nonlinear?
Non-linear.
Non.
Linear.
Good.
It's not-
Non-linear. And why is it not linear?
Because the rate of change is not the same.
Beautiful. The rate of change is not, what's that magic word?
Constant.
Constant. Good. Good. Would anyone like to share what they got for the first rate of change?
I got 243.
Good. 243.
Same.
And then if anyone would like to share, what did you get for the second rate of change?
486.
486. Good. So right away, you can tell these are two different numbers. This is definitely not linear. Did anyone notice a different pattern that might have been going on?
Yeah. Every time you subtract, you get the first number.
Yeah, so if you notice, the rate of change from here to here was 243, which is this first number. The rate of change from here to here was 486, which is that one. Can anyone think of a different pattern that like maybe we're not adding the same number, maybe something else is going on?
The number's doubling.
Yeah, they're
Multiplying by 2.
yeah,
It's a quad.
you got it. Multiplying by 2, they're doubling. So here it was times 2, times 2, times 2. So if you check, you'll see that this is actually doubling each time. And so I know that we like to know the different words for different types of patterns. This one is not linear. It's not quadratic either. This one would be called an exponential function.
Miss,
Mm-hmm.
when would you know not to divide the numerator by the other numbers?
When would you know not to divide the numerator? So do you mean like this type of pattern where it's multiplying?
Yeah, when you solve the problem for the thing, when you do the subtraction, how do you know not to divide for certain problems?
Okay, so for example, let me just do the first rate of change so I can kind of understand what you're asking me. So like if I was doing the whole m equals 486 minus 243 over 1 minus 0, right?
Yes.
And then you get 243 over 1. You're always going to divide at this step. There's not going to, I'm never going to say don't divide. You always divide. It's just that 243 divided by 1 is just 243. So I am dividing. It's just that I'm dividing by 1.
Then is it like that for all the other ones then? Because I did that and I kept dividing and I kept getting the same number.
Right, because you're dividing by 1. So anytime you divide by 1, you just get the same number that was in the numerator. But matter of fact, let me show you an example when you wouldn't get 1 in the denominator. So let's go ahead and actually do letter B now, because you'll see in letter B, it's an example of when you would have to divide by a different number. So in letter B, it's asking what is the average rate of change from day 2 to day 5? So I'm still going to use the rate of change formula. It's just that it's telling me which 2 points to look at. So I'm going to do the rate of change from 2 to 5. So what's my y2 going to be? Y2.
7,776.
Good. 7,776. Y1. Which one's Y1?
972.
Good. 972. And then X2
5.
is 5. And so it's going to be 5 minus 2. All right. What's 7,776 minus 972?
6,804.
6,804. And then 5 minus 2 is 3. So Chloe, notice now my denominator is a 3. So when you divide, you're not going to get the same number that you had in the numerator because now you're dividing by 3. And when you divide by 3, what do you get?
2,268.
Good. 2268. And what are my units, guys? Anyone can answer this one.
Cells per day.
Cells per. Good. Cells per day. Let me move this over. Cells per day. Perfect. Okay, so Chloe, I just want to make sure, did that clarify your question?
Yes.
Awesome. All right. Any questions on this whole problem? Any remaining questions?
Are there going to be more questions where there's like 2 steps?
In today's class, probably not. I don't think so. No, the rest of them are just straight up, multiple choice questions. So here's this is like basically what something like this would look like on a test where it just asks you, is this linear? Okay, so you'll probably have like a couple of tables to look at and you'll have to do the linear test to all of those tables. So what does that mean? We're going to check 3 different points for table number 1, or table A, let's call it. Check 3 different points for table B, and check 3 different points for table C. Now here's the cool thing, guys, is that it doesn't matter which 3 points you check. So let's say you're like, oh man, I don't want to deal with negatives today. Like negatives are not my best friends. I want to skip those numbers. That's fine. You could check this one and this one, right? You could check this one and this one. So what I'm saying is you don't necessarily have to do the first 3 points, especially if you see numbers that give you trouble. So like if you see this fraction and you're like, oh, I do not want to look at that. I don't want to pretend it doesn't exist. That's fine. You don't have to check that point. You can check any other 3 points. But still, what you're looking for is to see if you get the same answer for rate of change, constant rate of change. So do I have any questions before you guys try this one out? Cool. I'm going to put the poll up. So you go ahead and answer it in the poll whenever you get your answer. And I'm going to give you guys about 4 minutes because this one will take a little bit longer. So 4 minutes begin now. Go ahead.
Miss Lopez, we can pick 2 questions, right? Or is there just one?
There's only one. Only one of these is going to be linear. About a minute left. I have 5 answers in the poll. I know some of you guys are not on the Zoom if you're in the classroom, but anyone who's on Zoom, I want you to answer the poll. About 20 seconds left. I have 9 votes. And that's time. All right. So here we go. Here is my results. The winning answer was answer choice B, and that is the correct answer. So let's take a look. So B was correct. G of x is linear. The others are not. So if you were to look at B, and let me start with, I'll do these 2 points first. So I would have 1, so m equals 1 minus -2 over 2 minus 1. Remember, double negatives become a plus sign. So this would be 1 plus 2 over 2 minus 1. 1 plus 2 is 3. 2 minus 1 is 1. I get 3. If I check the next 2 points, it's a little bit easier because I don't have any more negatives, but I would have 4 minus 1 over 3 minus 2, which is 3 over 1, which again gives me 3. So I'm 2 for 2 right now. I'm going to check one more time just to be perfectly sure. My third set of points would be 7 minus 4 over 4 minus 3, which is 3 over 1, which is 3. So I got 3, I got 3, I got 3. That means that this one is definitely linear. You might have also noticed that the pattern on the right hand, so from -2 to +1 is +3, +3, +3. So again, you might notice that pattern, but it's always good to double check using the formula. All right, so that's why B was correct. Did anyone notice what pattern is going on in answer choice A?
The multiplication one.
Yeah, this one is
Multiplying by 3.
Yeah. This one's multiplying by 3. Instead of adding, it's multiplying by 3. And does anyone remember from the previous slide what this type of function is called when it's multiplying? Did anyone write it down?
X plus something.
Exponential. Yeah, so this one's exponential. So we know it's non-linear because it's exponential. And then did anyone notice the pattern here?
No.
Let's see what we have. So in the first pattern, I have plus, what happens? +1. Because from -1 to 0, it's +1. Then I have plus what?
3.
3. Then it's plus.
Oh, the patterns all add odd numbers.
Yeah, because this one's +5 and then this one's +7. Does anyone remember what this one is called?
Quad something.
This
Quad
is
something.
Yeah, Q, quadratic. Quadratic. So again, that doesn't matter too much for now. We'll have plenty of time in January and February to learn about these types of functions, but it's good to, ahead of time, it's good to kind of understand what they mean. So linear, and then the other two were non-linear. This is our last problem we're going to do together. We're probably going to end a little bit early, so I'll let you guys have some time to get started on some independent work. But here's our last problem. Can I have a volunteer read? Actually, Samantha, you have to read because it's about you.
Okay, fine. Each table below shows the time and distance Samantha and her friends traveled on 4 different road trips.
You can
In which
drive,
table?
Samantha? Oh my goodness, you can drive already? That's crazy.
In which table is there a linear relationship between time and distance?
All right, so this is a very similar problem. Go ahead and see which of those 4 is going to give me a linear relationship, a linear function. There's your poll. Answer it when you're ready. 4 minutes on the clock. About 2 minutes remaining. I have 8 answers so far in the poll. 8 people have answered out of 17. Thirty seconds. Still waiting on about 6 people to answer. 30 seconds remaining. All right. All right, so let me see what's going on here with the poll. We got 11 people voted. Anyone want to last minute put in their answer? Going once, going twice, and that's it. Okay. All right. So we were a little bit divided this time, guys. Take a look. We had kind of all over the place. So even though D was the most popular answer, it only won by 1 vote. So I definitely want to check this one out because this was a little bit more challenging, and I'll show you why. Okay, so let's take a look at each of the tables. Let's start with A. In A, the first thing I notice is that what's the pattern of the X values? Is that going at a nice constant pattern?
Yes, miss.
Yeah, right. It goes 2, 4, 6, 8. So that's cool. And then you might notice that the numbers over here might be following a pattern, but again, these numbers are not easy numbers. So I do want to check using my formula. So my first set of numbers, I have 220 minus 120 over 4 minus 2. What's 220 minus 120?
100.
100. And then 4 minus 2 is 2. So I get 50.
50.
Let's check the other two. Now I'm going to check between 4 and 6. So I get 340 minus 220 over 6 minus 4. What's 340 minus 220?
120.
What? Say that again?
120.
120 over 2, which is?
60.
60. So right off the bat, I got 50 for the first two. I got 60 for the second two, which means this is already not linear. Okay. So that was my answer choice A. Nobody chose answer choice B, and it's wrong, but let me just show you why. So this is going by ones, which is good. That means I can kind of just see the pattern now. And the pattern, how much is it adding the first time?
$80.
80. So this is plus 80. What about the second time around?
90.
90. Oh, so already this is not constant. So nobody chose B, but I just wanted to show why B is wrong. All right, now what about C? In C, something important to notice is what's going on with the X values. Are they changing in a constant way?
No.
No, right? It goes 2, 3, 5, 6. So it kind of skips the 4. So for this one, it's important to use the formula, because if you don't use the formula, you might not notice the pattern. So here we go. So I get 240 minus 160 over 3 minus 2. 240 minus 160 is
80.
80. 3 minus 2 is 1. So I get 80. Second 2, 400. Say that again? What did you say?
I think she said if you can hear her.
I can hear you very, very faintly. Okay. So 400 minus 240 over 5 minus 3. So what's 400 minus 240?
168.
160, yeah. And then 5 minus 3 is 2. Okay, but now I have to divide. So what's 160 divided by 2?
80.
Also 80. And I'm going to check one last time. I have 480 minus 400 over 6 minus 5. What do I get in the top? In the numerator, what do I get?
80.
80. 6 minus 5 gives me 1. So this turns out to be 80. So here, even though the pattern you might not have seen the pattern by looking at the table, when you actually do the work, you notice that this one is linear. So that's what somebody was asking, like, do you have to use the formula every time? Yes, because the formula will show you things that you might not notice by looking at the table. Because if I look at the table, I see, okay, this is plus 80, this is plus 160, and this is plus 80. So you might not think that that's linear, but it's because of the weird pattern in the x values that you have to double check, and you have to use that formula to figure it out. Okay, I know we have only a couple more minutes left, so just very, very quickly, I'm going to show you why D is incorrect. It might look like it's linear because you look at the pattern and you're like, okay, that's plus 75, that's plus 75, that's plus 75. Cool, I'm done. But what's going on in the x values? Is that constant?
No.
No, it skips around. So you have to use the formula, and very quickly I'm going to use the formula just for the first two. So I have 150 minus 75 over 2 minus 1, that's 75. But then when you do it in the second two, 225 minus 150 over 4 minus 2, 225 minus 150 does give me 75.
But it's divided by 2.
But it's divided by 2. So really this is 37.5. So you have to be very careful because if you look at and you see a pattern, you might think it's one thing. But remember what I said from the beginning. I said the formula does not lie. The formula is your best friend, and it'll always tell you if you have a linear function or a nonlinear function. So this one was definitely a little trickier, but does anyone have any final questions before we go?
No.
All right, guys.
Do we have homework?
Good question. So there is no homework tonight, but I will be assigning homework tomorrow. Okay, so for tonight, there's nothing, but just be aware that you will be getting homework tomorrow. So that's it, guys. We're all done. Very good job today. There was a lot of participation. You guys were doing really, really well today. I love that. So go ahead and make sure you keep that up for the rest of the week. Have a great night, and I will see you guys tomorrow.
Bye, Ms. Lopez.
Bye. Bye-bye. Bye, guys.
You have this? Yes, 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 yes. Shake your head, yes. So I can leave it?